Hello, AP Chemistry, and welcome to Chapter 20, our last chapter of the year, and a great chapter to end with because it does incorporate so much review stuff. So you'll be able to sort of see, like, ooh, I need to refresh on that, I need to refresh on that. So it's a great chapter, and it's fun, and a lot of it is stuff that you already see in life. Just we're going to talk about the chemistry part of it. So anyway, chapter 20, electrochemistry. First two sections, basically a review. So for example, here we have some zinc and we have some hydrochloric acid. And when we add the two together, we already know single displacement. We're going to produce some zinc chloride and some hydrogen gas. Now, going back to that question in your guys' book, right, we see bubbling and we see steam here. Why is that? Right, bubbles, if you had simply said hydrogen gas, that would be sufficient, right? But that doesn't explain this part, right? How do we get to that? Right, ding, 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 right? This process must be exothermic, right? Exothermic to the point that water is actively being heated and turning into gaseous water, right? Which is why we have this up here, right? So if you also said that this might be the result of the water portion boiling, that would be okay too. Though if you just said gas, hydrogen gas, that would be acceptable. So anyway, that's what's happening here in terms of why it's in the chapter 20 book, right? Because we have a redox process, right? Going back to oxidation states, right? Something in its elemental state, oxidation state of 0. Here, we would come up with separate rules, right? Chlorine usually -1, this usually +1, right? Same thing here. Zinc is always +2 unless it's an element, right? This is an element at 0, right? So assigning oxidation states will allow us to determine what was reduced and what was oxidized. And we would know, yes, this is a redox reaction, right? Where something gives away electrons, something else takes those electrons, and that's what happens over the course of the reaction, okay? Next up. If we look at the next slide, here we have a redox titration, right? So we can take the concept of redox, right, the exchange of electrons, and wrap it up in something we're already familiar with, titrations, right? So we already know that up here, right, we have our, what? Right, our titrant, where here we have our permanganate ion, aqueous, right? An aqueous permanganate ion happens to be bright purple, right? Down here we have our oxalate ion, right? So here is my oxalate, which is this reactant, which means that this is in excess until we reach the equivalence point, right? So this is clear and colorless. This is bright purple. This is also colorless, right? Which means that, so again, what's the point of all titration? Right, the point of all titration is we need to be able to figure out the number of moles originally present in here. And in order to do that, we need to figure out how many moles of this are required in order to reach that endpoint, which means that we have to have a Q that says we have reached the endpoint. If we think back to acid-base titration, what we did was we added a chemical indicator, something that wasn't a reactant or a product, but it would change color when we reached the appropriate pH, right, or the appropriate concentration of H plus ions in solution, right? Here we're going to use color change again because that's the only way we can keep track of it with our eyes, right? But we're going to take advantage of the reactants and products in solution, right? This is colorless, colorless. This is the only thing that has a color, which means that as we add that, right, it immediately reacts, right? Once we add that, it immediately reacts until we reach the endpoint where both of these are completely gone. After that, once we add that next drop of permanganate, right, after the endpoint, there is no more oxalate, this is called oxalate ion to react with it. Therefore, we then get a buildup of permanganate and we see a color down here. Okay, so we're still marking it the same way, just we're not using a third party to do it, right? Anyway, also a redox reaction. Thinking back to why this is in your guys' textbook, right? This is in your guys' textbook to talk a little bit more about how to balance a redox reaction, right? So here you'll see, like your book says, right, we often have things like H pluses and waters. Hydroxides are also common. Oxygen can be present, right? And that shouldn't be unfamiliar, right? If you think back to biology class, if you think about your electron transport chains and all those little cycles that you memorize, right? Electrons are transported often, right, for different processes, right? But we have to have a means of transporting them, right? And redox reactions are the way to do that. We just need to have species to carry them, right? Electrons don't exist without being attached to something, right? So anyway, so if we look here, your book goes through the steps to balance a redox in either acidic or basic solution. And like it says in the outline, you don't have to be able to do all those steps, but you need to be able to look at some half reactions, right? So here we have a, oh, nope, nope. Here we have a half reaction, right? This is our what? Right, this is our reduction half reaction, and we know it's reduction because, right, I'm adding electrons. Here, this is our oxidation half reaction, and we know that because, right, we are producing electrons, right? And so what you'll be given and what you're responsible for being able to do is, given this reaction and given this reaction, you need to be able to put them together and figure out how to come up with a whole balanced reaction, which really the key there is, right, balancing the exchange of electrons, okay? All right, next slide. If we take a look here, just in one more example of a redox process, right, and again, redox going back to the exchange of electrons, right, so here we have 2 electrons being exchanged from the zinc to the copper 2+, so that the copper is reduced, the zinc is oxidized, right, and the exchange of electrons is direct, right, as in they go directly from the zinc to the copper, right. What we're going to talk about in pretty much all of chapter 20 is how we can take those electrons and make it so that way they do work on the way to their destination, right? Which is the crux of all electrochemistry. All right. Again, if the assigning of oxidation states is, very fuzzy, I suggest you review that from chapter 4. Other than that, thanks for listening. Be good, and I will see you soon. Bye.